Hello everyone. Today we are trying to understand modules. Module is one of the fundamental algebraic structure in abstract algebra. Module is nothing but a generalization of the vector space concept over a field. Before defining module, let us revise definition of vector space. Vector space, a non-empty set V is said to be a vector space over the field F if V is an abelian group with respect to addition. Alpha plus beta times V is equal to alpha times V plus beta times V. Alpha times addition of two vectors, that is V1 plus V2, is equal to alpha times V1 plus alpha times V2. Alpha times scalar multiplication of beta and one vector beta V is equal to alpha into beta times the vector, that is V. And last condition is 1 times V is equal to V. So if any non-empty set V will satisfy these conditions, then that structure is called as a vector space over the field F. Here alpha and beta are the members of F, therefore they are called as scalars. And all these V, V1, V2 are the members of V, therefore they are called as vectors. And here beta into V, it is called as this multiplication is called as a scalar multiplication. Now let us define module. So module over ring. A non-empty set M is said to be module over the ring R if M is an abelian group with respect to addition. R times A plus B is equal to R times A plus R times B. R plus S times A is equal to R times A and R times B, S times B. R times SA is equal to RS times A. And this is true for all AB belongs to M and RS belongs to ring R. Here product SA, where S is a member of R and A is a member from M. So therefore this is called as it is here this product of elements of M and scalars from R is distributive over the addition operation, and it is compatible with ring multiplication. Now after that, here first of all we will discuss differences between vector space and module. In vector space, scalars are from a field F, and in module, scalars are from the ring. The second difference is all vector spaces have bases. Not all modules have bases. Some modules has a basis, and if the module has basis, then that module is called as a free module. Third difference is vector space is simple structure than the module, while module is quite complicated structure than vector space. From these differences we can understand that not all modules have a basis, and those have bases, they won't necessarily have well-defined dimensions. So we may say that vector spaces over vector spaces are particular case of modules, and on the other hand, vector spaces are lovable because they have simple and straight properties which made very convenient study of vector spaces. That's why I made statement that modules are quite complicated than the vector spaces. Now, we will see some trivial examples of modules and try to understand their connection with vector space. The first example is if F is a field, then F itself is a vector space over F, and also F is a module over the same F, and both vector space and module are identical. We know that every field is a vector space over itself. Since field is always a ring, hence we must say that F is a module over a ring F. As you know that conditions in vector space and modules are same, therefore here vector space F and vector module F both are identical. Also, we'll try to understand another second example. If F is a field and Fx is a ring of polynomials in indeterminate x, then module over ring Fx, that means module over the ring of polynomials, is identical with a vector space over the field F. Okay. Now, over F combined with linear map from module to vector space. Now we'll see another example, and we're trying to solve this example. Show that every abelian group G is module over ring of integers. Here we want to solve. Here in this example, G is already an abelian group and R is a ring of integers. Therefore, we have to mention their names here. We will declare the names. Let G be an abelian group, and let R be a ring of integers. After that, since G, who want to become module here, is already an abelian group, therefore here we want to only show that, or we want to only prove three conditions. So that's why first of all we will consider some elements from G. So let two elements A, B are the members of G, and two elements R and S are the members of ring of integers R. And the first condition we want to show that is we are putting in the claim is to show that TST means to show that R plus S times A is equal to R times A plus S times A. Now how to show this? First consider the left hand side, that is denoted by LHS. So we have R plus S into A. Now note that R and S both are the members of a ring, and ring is a ring of integers, therefore R and S both are integers, and we know that addition of two integers is again integer. So try to understand this. I will explain here. Suppose I am writing 5 times A, and that 5 can be written as 3 plus 2 times A. Okay, so 5 times A means A plus A plus A plus A plus A 5 times. And if you notice that the first 3A, if we put the bracket, then it is 3 times A and it is 2 times A. Same thing we will apply here. Since R plus S is an integer and the integer times A means A plus A, we can add this A up to R plus S times. Is it right? Now its meaning is A can be added R times as well as A can be added S times. So we can put the bracket and A can be added R times in one bracket, plus in another bracket A can be added up to S times. And therefore we can write the first bracket is R times A and the second bracket is S times A. And this is your required right hand side, and this is true for all elements of G and S. So first condition is over now. Now we will prove another condition, second condition. So here our claim is to show that R times A plus B is equal to R times A plus R times B. So again consider the left hand side, it is R times A plus B. So it is R is integer, therefore this bracket A plus B we can add it up to R times. So it is summed up to R times. Now the bracket can be added R times, that means the terms inside the bracket or also can be added R times. Therefore the first term A can be added R times, and the second term inside the bracket, that is B, can be added up to R times. Now A can be added R times means it is R times A, and B can be added R times, it means R times B, and this is our required right hand side. So second condition is also over. Now we are going to prove the third and last condition, and we will put in the claim, that is to show that R times S times A is equal to R S times A. We will select same criteria to prove this. We first consider left hand side, R times SA. Now what is your understanding about this multiplication inside the bracket? I am putting R as it is, and this S times A means we can add this A up to S times. For the sake of convenience, this square bracket I am denoted by capital A. Therefore we can write this step as R times capital A. R is an integer, therefore we can write A plus A up to summed up to R times. Now this A is a bracket containing small a addition up to S times. Therefore this is a summation of AS times, this is a summation of AS times, and this bracket added up to R times. So ultimately the small a can be added RS times, so it is RS times of A. So this is your right hand side, and therefore it satisfies all the conditions of the module. Therefore this example where the G is a module over the ring of integers R. Now we'll see some another trivial examples. If R is any ring and n is a natural number, then the Cartesian product Rn is a module over R. Here in particular, when n is equal to 0, then R0 is singleton 0, and this is a trivial module, so it is a example of trivial module. And when n is equal to 1, then R itself become a ring, and we know that R itself is a module over the itself R. Here scalar multiplication is nothing but a multiplication in the ring. Now second example, if R is a ring and I is an ideal of that ring R, then that ideal is a module over the ring R. Now we will see a definition of submodule. If M is a module over the ring R, a non-empty subset N of M is said to be submodule of module M over R if it satisfies some condition. The first condition is N is a subgroup of M and the multiplication R into N. So R is a member of ring that is called as a scalar, and N is a member of N who want to become a module, submodule. So this multiplication will be again a member of N. If this happen, then that N who is a subset of M is called as a submodule of M. If A and B are submodules of M, then prove that intersection of A and B is also a submodule of M. So this we want to prove here. So here our target is, if we read the example or theorem, here we want to show that A intersection B is a submodule of M. So before that, already it is given to us, given that A and B are submodules. So that's why all the elements of A as well as B must satisfy conditions of submodules. So we can enjoy, or we can use the conditions of submodules for A and B. Now our aim is to show that, claim to show that A intersection B is submodule of M. So according to definition of submodule, if we want to show that any subset or any set is a submodule of M, then we want to show that that is a subset of M first, then a subgroup of M, and then that condition R into N belongs to A intersection B. So here A and B are already submodules, therefore they are already subgroups of M. So we can give the reason that A and B are subgroups of M because they are submodule of M. And we know that, here mentioned, we know that intersection of two subgroups is again a subgroup. And using this result from group theory, we can declare that A intersection B is a subgroup of M. Now only thing remaining is take one element from that set who want to become submodule, that is A intersection B. So I am considering that let X belongs to this. According to definition of intersection, this X is a common member of A and B. So X belongs to A and X belongs to B. Now you take one element from the ring, let R belongs to R, and you consider the product Rx. Now X is a member of A and A already is submodule, therefore Rx belongs to A, and this is a member of B and B is already submodule, therefore Rx is also belongs to B, and therefore we can put here N. Therefore a common element Rx belongs to A and B, and therefore Rx belongs to A intersection B, and this is true for all R belongs to R and X belongs to A intersection B. So A intersection B satisfied all the conditions required to show submodule of M, hence A intersection B is submodule of M. After that, we are going to prove another example. If A and B are submodules of M, then prove that, or then show that A plus B set, which is defined like this: addition of elements from A plus addition of elements from B is also submodule. So in the same way, we can prove this. For this, we want to show that the first claim is to show that this a plus b is a subgroup of M. We know that from the group theory, to show the subgroup we need two conditions. One is a closure property and another is inverse law. But now here I am combining both the conditions. Therefore, I am considering two elements, let x and y belongs to a plus b, and we have to show that x minus y. Actually, if we have taken plus sign here, then it will only a closure property, but we want to show that simultaneously the inverse law. Therefore, I am considering x minus y. And if we show x minus y also belongs to a plus b, then it will become a subgroup of M. So now, how to show that x minus y is a member of a plus b? We know that what is x? X is a member of a plus b, and we know that in the set a plus b, every element can be written as addition of one element from a and one element from b. So we can write particularly for x a1 plus b1, where a1 is some element from a and b1 is some element from b, minus y can be written as a2 plus b2. We have to mention here what are the for some a1 a2 belongs to a and b1 b2 belongs to b. Note that a and b both are submodules of M. Now just simplify these two brackets is equal to a1 plus b1 minus a2 minus b2. Okay, by using the associative law, we can write the a1 minus a2 plus b1 minus b2. I want to know that a is a submodule, therefore it is a subgroup, and therefore a1 minus a2 must belongs to a. Similarly, b is also submodule, therefore it is a subgroup, therefore b1 minus b2 belongs to b. So the first bracket is a member of a, capital A, second bracket is a member of capital B, therefore we can say that it is a member of a plus b, and hence x minus y belongs to a plus b for all x and y belongs to a plus b, and hence we can declare that here a plus b is a subgroup of M. Alright, after that, to show the submodule, we have to take one element from a plus b. So let us consider, let x belongs to a plus b and one element from the R. So let a small r belongs to R. And now we have to show that R into x is member of a plus b. So this is we want to show that. So R into x, where R into x is a member of a plus b, therefore we can write a plus b for some a belongs to a and b belongs to b, by definition of a plus b. Now a and b both are the members of module, therefore we can distribute this r over the addition, so we can write the ra plus rb, and therefore since this ra since a is a submodule, it is a member of a and this is also a member of b, therefore ra plus rb is a member of a plus b, and ultimately we can say that Rx is a member of a plus b for all r belongs to r and x belongs to a plus b, and hence a plus b is submodule of M. Submodule of M. Okay, after that we are going to define some new concept, that is a homomorphism for the module. A mapping f from module M to module N is said to be a homomorphism of M if that f satisfies this condition. F of Ra plus S is equal to R times f of A plus S times f of B, and this condition must be valid for all the elements Rs from R and AB from module M. Now using this definition, we have to solve one example. If F is a homomorphism on a module M, then prove that a set containing some elements from the module M whose image under the function f is 0 is a submodule of M or R. Now, to become a submodule of M, the A must be a subset of M, and we know that clearly all the elements of A are coming from M. Therefore, clearly we can say that A is subset of M. Now, next target is to show that A is a subgroup. Claim to show that A is a subgroup of M. Again, we have to take two elements. Let x and y belongs to A. These are the members of A. Therefore, they must satisfy the condition on A. Therefore, f of x is equal to 0 as well as f of y is equal to 0. And now we have to show that x minus y is a member of A. This want to show that. So to confirm the x minus y will be a member of A, just put this x minus y inside the function and try to check whether its value is 0 or not. But f is a homomorphism, therefore using the definition of homomorphism we can write this, and already we know that f of x is 0, 0 minus 0 is 0, therefore x minus y belongs to A for all x and y belongs to A, and therefore A is subgroup of M. Now the last condition is to show that this A is a submodule, and for that take one element from the A, and this implies f of x is equal to 0 and one element from the ring. And now to show that this Rx multiplication is also a member of A. Any element will become a member of A if that member will have the image 0 under the function f. So just I am putting this Rx inside the f. F is a homomorphism, therefore we can write this, and f of x is already 0, therefore we can write this as 0. And therefore Rx is a member of A for all x belongs to A and R belongs to R. And therefore A is submodule of M. So this is something related to module. So stay healthy, take care, bye bye.